Hello there. So this is video number 1 of section 2.3. And what this is going to do is summarize a lot of the information we learned last section, but also pretty much every section sort of starting with 1.4 up until now. So granted, for a lot of that time, we've been talking about matrices which were not square, that is, had a different number of rows and columns. This theorem is only going to be talking about square matrices, so n by n matrices. And what we're going to do is basically list out all of the things that are equivalent to a matrix being invertible. Hence the name, the invertible matrix theorem. So what this theorem says is that if A is an n by n matrix, so again, same number of rows and columns, then the following statements are equivalent. And so what that phrase means is that either one of these statements, or if you can show one of these statements is true about a matrix, that means every single one of these statements is true about that matrix. Equivalently, if you can show one of these statements is false about a matrix, that means that all of these statements are false about that matrix. And so what this means is that we have the power to answer a lot of questions about not only a matrix, but also a linear transformation corresponding to a matrix, and potentially about a set of vectors, right? Because we can always take a set of vectors and turn them into the columns of a matrix and answer, for example, the columns of A span Rn is equivalent to saying, well, these vectors span Rn. So this sort of gives us the power to answer a lot of the questions we've been asking when we're working with square matrices, of course, and to sort of know how to answer those questions. So I think the big theme of this theorem is sort of described in part by B, because notice condition B is that A is row equivalent to the identity matrix I sub n. So remember, A being row equivalent to I sub n means that we can row reduce A and get the identity matrix. And so you could also alternatively name this theorem all of the things that you know about A if it row reduces to the identity matrix. So how does this theorem apply to you? Well, suppose you're given a matrix and you're asked to show that the columns of that matrix are linearly independent. Well, one thing you can do is you can row reduce A and ask, did it row reduce to the identity? If yes, then yes. If no, then no. You can also occasionally use these things to quickly check one another, right? So as we'll see in a second with an example I'm about to do, you might be asked if the matrix is invertible, but you might be able to tell from quickly inspecting the matrix that the columns of the matrix are not linearly independent, or that the columns of the matrix maybe don't span Rn, a few things. And so, what this also gives you the power to do is not necessarily always have to row reduce to the identity matrix to show one of these things is true. So, this is very, very important, because I think this very, very much summarizes, how do I answer a lot of the questions about matrices that I am being asked, right? So, I think these statements really do cover pretty much all of the questions about square matrices that you will be asked. And this sort of gives you a roadmap to saying, okay, how do I answer each of those questions? So, the answer is, at worst, you row reduce A, check, is it equivalent to the identity matrix? If yes, well, then all of these things, the answer is yes. If no, then to all of these things, the answer is no. So this is the invertible matrix theorem. I'm going to just conclude this video by giving a few short examples. A note on this, I think throughout the course we have, and I apologize if I'm repeating myself, but I think throughout the course we have been showing that a lot of these things already imply each other. So I know when we were talking about A being invertible, we were also showing how that implies these two things. And from these two things, of course, we get a lot of the other conditions. You notice J and K basically are just talking about invertible matrices, and we also showed L is something we get if A is invertible. So I don't want to talk too much about the proofs of these. It's possible on a homework or on a worksheet at some point I might include sort of a proof for you all to try, just because I think it's fun to sort of prove some of these things and show that some of these things imply each other. But I think, like I said, I think throughout the course we've actually already shown a few of these proofs already, and if we were to do every proof in this video would take maybe the rest of the semester. So, this is the invertible matrix theorem. Like I said, you can use this to answer a lot of the questions you will be asked about matrices. And so I just want to end with a couple examples of how we might use this to answer the question of whether or not a matrix is invertible. And of course, we will be referencing this quite frequently throughout the semester when we want to answer other similar questions. All right, so I'm going to actually ask a slightly different question than I was initially going to ask. So the original question was to determine if the following matrices were invertible. But remember, we can ask this question sort of about anything. So I'm going to say determine if the linear transformation T of A, which is going to be defined by matrix multiplication, is 1, 2, 1. And so we're going to do this for two matrices, and I'm going to show you how you can sort of, again, use this theorem and maybe occasionally use a few shortcuts to not always have to row reduce. All right, so 1 to 1, I'm going to put in parentheses here also invertible because they're equivalent statements, as we've learned. All right, so this matrix. All right, so one foolproof way of doing this is always just to row reduce this matrix. And so we can do that relatively quickly. Now I'm going to do a couple steps at the same time. So I'm going to do 3 row 1 plus row 2, and negative 8 row 1 plus row 3. And so at this point, I'm actually going to stop you, because at this point we can see that this matrix will, in fact, row reduce to the identity. I guess it's only a couple more. So 1 over 7 row 2, and then we do negative 5 row 2 plus row 3. And sure enough, we get the identity. So I want to give you a little bit of intuition as to how I could look at this matrix and immediately determine it was going to row reduce to the identity without having to do this. So notice, so this is actually called a lower triangular matrix, and we're going to learn later in the semester exactly why this can row reduce the identity. But so I sort of saw when we get a row, sort of a diagonal happening like this where I've got zeros above it, I could sort of tell that this 5 was just going to be easily turned into a 1, that it was going to clear out these two rows, the 7 was then going to clear out this, and we were going to be home free to the identity. So I could sort of see, like I could circle all the pivots and say these are definitely going to be pivots because there are already zeros above them. And so the fact that this matrix was lower triangular in this way is what we technically call it, although that's not really a definition we need yet. I could sort of see that this matrix was going to row reduce. So like a few tricks to occasionally save you from row reducing, but if I wanted to answer this question of whether or not this linear transformation is one-to-one, I could always, a foolproof way would be to row reduce. Notice I get the identity matrix. So using the invertible matrix theorem, because A is row equivalent to the identity, this linear transformation is one-to-one. Also is invertible, also is onto, and also all those other things. All right, so B. Now this one we can definitely do with not too much work. So all right, so we want to determine if the linear transformation is one-to-one. So one of the properties of the invertible matrix theorem is that the columns of A are linearly independent, and that the columns of A span are, in this case, R3. Notice A has a column of zeros, and so that actually immediately disqualifies it. So I'll give you one example. Well, so I think this actually immediately implies that these columns are linearly dependent, right? Because any time a set of vectors has the zero vector, this column is linearly dependent. So since 0 is a column of A, columns of A are linearly dependent. And so what this means is that A is not one-to-one and A is not invertible. So we'll say T of A is not one-to-one. And A is not invertible. Because remember, the invertible matrix theorem says that either if one of those statements is true, they're all true, but if one is false, they're all false. And so here, in order to show this matrix was one-to-one, I showed that just one of those statements was true and we were done. Here, I just had to show that one of those statements was false, and the zero vector immediately disqualifies this matrix from having linearly independent columns. And so that wraps up the video for now. I think we're going to talk a little bit more about kind of how we interpret this, especially on the linear transformation side of things this section. But yeah, definitely read over that theorem, sort of become comfortable with all of the implications of that theorem, because that is definitely the most important thing this section.